Good morning, everyone. Thanks for joining us on this webinar on a smart motor with CANOpen. The presentation itself is slightly longer than the last couple. We're at about 23 or so minutes on this. So feel free to ask questions throughout while it's running and we can get to those at the end.
Hello and welcome to today's webinar. Today we're looking at controlling a smart motor with Horner OCS over CANOpen. Let's get started. Let's look at our agenda for today. We'll start with a review of CANOpen. We'll look at different applications using CANOpen with OCS. We'll look at the basics and the configuration of CANOpen. There will be demonstrations throughout, and we'll finish with a Q&A session. CANOpen is a standard communications network that's based on the CAN chip. There are plenty of networks based on CAN, for example J1939 in mobile and automotive applications, and there's also the Horner C-SCAN network, which is used for adding I/O to OCS or having OCS communicate with each other over the network. As we compare CANOpen with C-SCAN, we can see that they were designed with two different things in mind, as CANOpen is a standards-based network focused on having components from multiple manufacturers talking to each other, whereas C-SCAN was focused on getting Horner components to connect as easily as possible, a plug-and-play approach. Now we'll look at the benefits of CANOpen with OCS. Interoperability is the main focus of CANOpen, so if you have a sensor or an encoder or a smart motor that you want to communicate to, CANOpen would be a good choice. It's good for motion control because it has a lot of capability at a fairly low cost when you compare it with other networking choices. If you're looking at adding I/O to an OCS or having OCS communicate with each other, C-SCAN is the best choice as it's plug and play. Now we'll look at why a smart motor and an OCS work well together. If you take a look at the level of integration on an OCS, there's a logic engine with built-in I/O, operator interface and networking in one compact package, all configured with the same software package. If you look at smart motors, there's the motor and the drive with the networking interface, all built into one component. It's also highly integrated. So it doesn't take a lot of complex integration to interface these two components and to provide a complete system with a minimum of components. Now we'll look at the different options when interfacing a smart motor with OCS. You could use the more old-fashioned step and direction approach, or you could go with a Modbus serial approach. These are both cost-effective and will both work well, but if you're looking for the next level of performance, the CANOpen would offer that. There are some other options as well. In some cases, these other options might seem a bit easier from a configuration point of view, especially when you're talking about Modbus TCP. However, those options generally come at a premium. When you look at smart motors, you'll find the Ethernet options are more expensive than CANOpen. The two CAN-port versions of the XL series OCSs, like the XL7 and the EXL10, support CANOpen as standard and have done for years. So if you have an EXL10 or an XL10 Prime, or an XL7 or an XL7 Prime, those have CANOpen available on the second CAN port. You can order CANOpen as a factory option for all the XL series and XL Prime series products that have a single CAN port. That's also true for the X5, which currently is the only micro series product that supports CANOpen. Now we'll look at some of the CANOpen basics, starting with the object dictionary. The object dictionary is just a list of parameters. A lot of variable frequency drives that, for instance, have Modbus support will have a list of their parameters along with a list of Modbus addresses. One thing that's a bit different with CANOpen is that it uses hexadecimal addressing, and it's not just an index, which is the equivalent of the address, but it also has a subindex, so it's organized a bit differently. One of the benefits of OpenCAN is that it has device profiles. So depending on the type of device that you're integrating, there's specifications that detail how that type of device should interface over CAN. So as an example, you'll find that there's a profile called CIA 402, which is highlighted on the list there. And that covers drives and motion control devices over CANOpen, and is where you would find smart motors from a category standpoint. So even though today we'll be looking at a nanotech smart motor, we'll see that the interface is going to be very similar for the other brands of CANOpen smart motor. So the main advantage of CANOpen is that these device profiles standardize how similar devices communicate on the network. Now we'll look at the different protocol types that are available as part of CANOpen. Starting with network management, which is a way for the current state of the network to be managed. It's usually managed by the master on the network, which in this case is the Horner OCS, but the network state can be one of several choices. When a network comes up, it's in the initialization state, then it's pre-operational, then it goes operational, which is where it does most of its work. And then if something goes wrong, the network will go down and be stopped. Heartbeat protocol is used to determine the health of individual nodes. So that's a protocol that's used over CANOpen for that purpose. And then there are different types of messages that are used to exchange data. There's a service data object, or an SDO, which is the message structure that's used to transfer messages as needed. So they're not set on a continuous basis, there might be a parameter and you need to change that on an occasional basis, then you can use an SDO for that. And then you have process data objects, or PDOs, which are continuous data exchanges that occur while the system is in run mode or operational state. And that's where, in most cases, a bulk of the data is exchanged. One other protocol is called the sync protocol, and we'll demonstrate that today. The sync protocol is an option which allows the master to send out a sync pulse periodically, which will allow PDO type messages to be exchanged on a periodic time schedule, maybe every 50 milliseconds or every 10 milliseconds. So that's the sync protocol that's available as an option. Now we'll look at CANOpen configuration in general, and as we get more specific, we'll get down to smart motors at the end and see how to do it in Cscape. Firstly, we start out by configuring just the basics. We don't recommend doing it all at once. Do the base amount of configuration, test it to make sure it's working, and then move on. If possible, use the default settings on the client for baud and ID. So for example, your application is one OCS and one SmartMotor, and to make things easy, use the default baud rate and default ID for that SmartMotor. Before you start, you always need to make sure you gather all your documentation and that you understand what's included in that documentation. And also, you're going to want to gather EDS files, which are a special file that you'll use as part of the CANOpen configuration, which will make it easier to take the data that you want from your smart motor. So the basic process, which we'll demonstrate here in a couple of minutes, is as follows. Firstly, select your baud rate and your CAN ID. Map those out, and you're going to make sure you get your EDS files gathered up and copied into the appropriate directories. If your slave that you're configuring, like a smart motor, has its own software for configuration, you should handle that first. And then once you go into CANOpen configuration on the OCS side, which uses Cscape, then you're going to have a series of steps we're going to go through. And we'll demonstrate those for you here in a minute. And again, the key is to configure a certain number of items and then do the testing. Now with smart motors, because there are standardized profiles available in CANOpen, one of the advantages is that a lot of the data addresses are standardized. So when you're talking about interfacing an OCS with a smart motor, especially if you're talking about positioning control, maybe you're going to move an object across the x-axis or something like that, then you'll find that the data is going to be the same from application to application. So what we have here is some of the data that is going to be important for a typical positioning application. With CANOpen now, there are hundreds of parameters available, and we're looking at the ones that are most requested and most required. Now we'll go into Zscape and we'll look at how to configure a smart motor. Here we have an already configured application which we'll review shortly, but first we'll open a new application, and we'll look at how to do this from scratch. So we select new, then we use a register-based approach for this example. So we have a new application that's blank, and we're going to start from the configuration area. We're configuring an XL7, and one of the advantages of the XL7 is that you can have CANOpen support available as standard on port 2. So we'll select CANOpen on port 2 and press the configuration button. And now the OCS can act either as CANOpen master or as a slave. And when you're dealing with a smart motor, the OCS is going to be the master. So we'll select that. And then we get into the configuration. So we'll start by configuring the OCS as a master, and then after we get to a certain point, we'll add in the slave, which will be the smart motor. We recommend that you use the defaults for ID and baud rate for the slave that you're using if those will work for you. So the default with the nanotech smart motor is an ID of 1, which means we don't want the master to have an ID of 1. So we'll assign a 127 as the master ID. The default baud rate for the motor is 1 megabit, and if the network is less than a few meters, that's not going to be a problem, and this network is, so we'll do that as well. For configuration, we'll just look at how generally you're going to configure the minimum. So one thing we'll check is the perform NMT, which is the network management that we talked about. So the OCS as master is going to be responsible for the network state, and so we want the OCS to automatically start the network to put everything into operational mode. So we make that check mark. The only other thing we want to configure here is a status register, so we'll assign %or1 to that. We're using register-based logic here and will require 4 consecutive word type registers for the master, and then for every slave there'll be another 16-bit word as well. Now there are lots of other things to configure, so we'll go through that now. Under device type, that's just informational and there's nothing to configure there. For special function objects, we only need to configure this if we're going to use the sync protocol. Remember, the sync protocol is an optional approach where the master can send out a sync pulse periodically that all PDO messages are timed with. So here we want the master to generate the sync message, then all that is left for us to configure is how often the sync message goes out. So by default, it goes out every 500 milliseconds, but we want to go with 10 milliseconds, which is 10,000 microseconds. And then finally, we have to configure what portion of that 10 milliseconds do we want to send 6 messages in, and we'll say the first half, or 5,000 microseconds. So that's all we need for special function objects. Under error control, we won't use note guarding, we'll use heartbeat, and we want to generate a heartbeat every 500 milliseconds. Later, we'll add in a configuration time or a heartbeat time for monitoring the heartbeat of the SmartMotor, but we haven't added in the SmartMotor, so we can't do that yet. There's nothing to configure under SDOs, and then we have PDOs, which are the messages that we're going to exchange at runtime. So the only configuration we'll do on PDOs with the master is to add a couple of transmit PDOs to the master. You can't map data in and data out from device to device on CANOpen until the device that's transmitting the data has been configured with at least its transmit PDO. So we'll add 2 entries here for transmit PDO. So we press the button the first time, we don't want to disable PDO, so we uncheck that. Now under the object ID, we want to use the default value as much as we can. So we'll use the default value for the object ID for this transmit PDO, and we'll make this transmission signal to be based on the sync pulse. So every time there's a sync pulse, that's when we're going to transmit this PDO. And then we'll add another one that is pretty much identical to what we created, except the object address is slightly different. We're still using the default, so we just copy the value from here to here. It's still synchronous and based on a sync pulse, and now we've added the transmit PDOs for the master. So now we've configured the master as much as it needs to be configured for now. Now we'll add the SmartMotor, so we press the Add Slave button here, and then that starts the slave configuration wizard. The node ID of the slave is going to be node ID 1, which is the default for the SmartMotor. Then we'll load the slave from its EDS file, which we've previously loaded into Cscape in the appropriate directory, and so we'll utilise that. So we'll press the next button here. So we want to use the default settings for sync, and we don't want to do anything with timestamping. The default settings for emergency protocol are also okay. And then from a heartbeat standpoint, just like the master, we'll have the motor generate a heartbeat every 500 milliseconds, and we'll check from the master node, which is 127, to make sure we receive a heartbeat at least once per second. So that's how we want to configure the heartbeat monitoring. So we want to have the standard object IDs supported for SDOs, and then we do want to have a couple of transmit videos with the motor, so we'll set that at 2, and we could go up to 4. We'll use the standard object IDs again as much as possible. For mapping data back and forth, we prefer to just use standard %or registers rather than global mapping, so we'll uncheck that option. We do want to be able to receive PDOs from the master. In this case, remember, we're configuring the SmartMotor. And again, just like on the data going the other way, we usually like to avoid global data. So we'll press the Finish button now. So once the EDS dialog pops up, now we can select the manufacturer of the device we're adding, and that's Nanotech. The device is the PD4, and profile is the only one available here, so we'll say OK, and now the Nanotech SmartMotor has been added. So now we'll configure the details for that. Firstly, we'll make this a mandatory slave, which means if the slave is powered down, we won't send the CANOpen network into operational mode because there's no point as a critical slave is not up and available. Up here are all the different services which could be enabled. The only ones we'll enable are the Aero protocol, the PDO and the SDO configuration. This means that we're able to, from Cscape, tell the SmartMotor what data we want to exchange using PDOs. So those are the only 2 we'll configure on this page. And just like that master, there are other pages to configure. So nothing here on device type as it's just informational. For special function objects for the master, we had to configure sync, but as a slave, we don't have to configure anything. Error control object is already set up because the wizard is set up, so we're generating heartbeats every 500 milliseconds, and we're checking to make sure the master, as node 127, has sent us a heartbeat at least every 1000 milliseconds. There's nothing to configure under service data objects or SDO messaging. Now we'll look at the PDOs. So under the transmit PDOs, we have said in our wizard configuration we want to transmit PDOs, and there they are. So we'll start from there to add the details as to what motor parameters we want to transmit from the motor back to the OCS. We'll start with the first PDO message, and every PDO message can have as much as 8 bytes of data in it, so if we keep our data below 8 bytes, it will all work. So looking at the first PDO again, this is the data that the motor is going to transmit and will be received by the OCS in a % or a register. So we highlight the first PDO and press Add Entry. And now, because we're talking about the SmartMotor, we can press the Set from EDS button and we can see all the motor data that's available for us to transmit back to the OCS. We'll start with our status word, which is 6041, and that's the hex address. We can see that's an unsigned 16-bit value, so we need to make sure that the matches are here and we can say OK. The next one we'll add, we'll choose the current mode of operation that the motor is in because we want to verify that it's in positioning mode or find home mode, and so that is parameter 6061, and we can see that it is a signed 8-bit value. Now we need to change this to a signed 8-bit value, and now we configure this PDO in terms of what data is being transmitted. Next, we'll do the same thing for the second PDO. We'll add an entry this time, and we're going to add the actual value of the position. So the SmartMotor is at the position of 6064. So we'll scroll down for that. Here it is, and we see that it's a 32-bit value. So we must set signed 32. And then the final one we're going to send as part of our demonstration today, we're going to send our actual velocity, which is 6044. And when we get to that, we can see that it is a signed 16-bit value. So again, here we pick the data that we want and we make sure that the format is appropriate. So this is the data, and it's going to be broadcast through a PDO message back to the OCS. So now we need to go back to the OCS, which is the master, and go to its receive PDOs, and configure where in OCS memory we're going to map this data coming in from CANOpen. So we start by adding receive PDOs, and then we press the add entry button when we get a choice of which we want to add. So the OCS itself is going to be transmitting 2 PDOs, but we don't want those, and the slave is going to be transmitting 2 of its own. So the first transmit PDO from the slave is going to correlate to the first receive PDO with the OCS. This 2 does not indicate node number 2, it just indicates that the slave is second on the list after the master. We'll press select here, and then we'll add the second one again. Then, one by one, we'll map where the data coming from the CANOpen slave from the SmartMotor is going to end up in the OCS memory space. So we highlight the first receive PDO because that's where the master receiving the data. Then we press add entry, and we don't use the set from EDS button when we're just mapping data back into the OCS. All we do is type in the register address number where we want the data to come in, and then we make sure that we get the type right. So the first thing that's coming back in is the first PDO and the status word, which is coming back in unsigned 16-bit format. And we'll choose to receive that data into register 1001. So all we do is type in register 1001 and make sure the format is right. And for the second parameter that's coming in that PDO, that is our mode of operation display, which is a signed 8-bit value. So we put that into %or 1002, and we make sure that we have signed 8-bit selected here, press OK, and then we'll finish this receive PDO as follows. So we'll add the entry here, and the actual position is a 32-bit value, but we put that into %or 1005, and we can put it wherever we want if it doesn't conflict with anything. That's going to be an unsigned 32-bit. And then the final one we add is the actual velocity that's coming in as a 16-bit unsigned. We'll put that into %or 1007, and 16-bit unsigned is still correct. So that's how we had to configure data being transmitted by the slave and received by the OCS as master. Now we need to transmit data from the OCS and we need to send it to the slave. We'll start on the slave side. So that will show us the data that we want to transmit to it. So we go to receive PDO on the slave side, press add entry and select the master's first transmit PDO, and then we'll do the same for the second one of the master's transmit PDO. Then we'll determine what data we want to receive into the motor. The first thing we're going to receive is the control word, so we'll set from EDS, and then we're going to find the control word, which is 6040 unsigned 16-bit. Next, we'll configure the mode of operation that's being commanded to the motor, which is 6060, and that is an 8-bit signed value. Next, we'll go to the second PDO. We can see that with each of these PDOs, we've been well below 8 bytes of data as we haven't filled them up, but we just want to establish and put some data in a few PDOs. Now we'll configure the second receive PDO on the motor side. The next piece of data we want to receive from the OCS is the target position, which is 607A, and is assigned a 32-bit value. You can look these addresses up in the user's manual. And then finally, we'll receive in our profile velocity, which is 6081 and is an unsigned 32-bit. So make sure we have unsigned 32 configured, and there we go. So this is the data we're receiving in from the OCS that tells the motor how fast to go, what position to go to, etc. So the final part of the configuration here is we're going to the transmit PDO of the OCS to configure which registers the data that we just configured in the slave is going to originate from. So we select the first transmit PDO for the master, and this is the controlled word unsigned 16-bit. We're deciding as part of the application network map we'll have this transmitted from register 1011, and then next we send our mode of operation, which is signed 8-bit, and we'll originate that from %or 1012. Next we have our 2 pieces of data to descend from OCS to the motor, and that is the target position where we want the motor to move to, which is an unsigned 32-bit, and we'll have that originate from our 1013. And then finally, we have the profile velocity or the velocity command, which is an unsigned 32, and we'll send that from %or 1015. So now we're basically configured, and it's a long process, but if you do it systematically, it's just a matter of following the steps in order. There's one last thing to do, and so we'll go back up to the master configuration. And then, under the error control object, we'll make sure that the heartbeat monitoring is the way we want it. So we're generating a heartbeat every 500 milliseconds. At the time we configured this, there was no slave. Now there is, but we don't want to monitor the slave heartbeat every 500 milliseconds. We want to monitor it every 1000 milliseconds instead, because if it's a little bit late, we don't want to throw a flag. So now we're done with the configuration. So again, that's the process to go through for a SmartMotor. If you have a positioning application, you can follow the same steps. Now we'll see another option. So we'll show you an application that was previously created. Now we'll look quickly at what these different pieces of logic do. So here we're looking at an initialization section. We have a CANOpen section where we have the standard state machine for CANOpen that every CANOpen smart motor and servo drive is going to follow. Also in this section of code, we give you the ability to send and receive SDOs. So if you have a parameter you want to change from the screen of the OCS, just occasionally, you could do that. And then we also have logic in here that's decoding the status information coming back from the OCS on CANOpen, so you always know the status of the CANOpen network. The main section is where you would put your logic, and we also have a change mode routine, and there's an enable drive section, because if you want to move a motor, you have to make sure that it's enabled. There's a find home routine, there's logic in there for performing absolute moves, and then there's also logic here for jogging. So everything is very well documented. Now we'll have one last demonstration. So here we have this demo program that we saw in Seascape a minute ago, just in a simplified form. So here on this screen, we can easily move the smart motor. You can see here that we have the smart motor connected over CAN2, which is CANOpen, and then we have our target position, which currently is set for 4000 counts. This smart motor has 2000 steps per revolution, and its default acceleration is 500 pulses per second per second. So the target position is already set to 4000, which should be 2 revolutions, and if we start the move, you can see that we moved 2 revolutions. And if we go to a target of 0, we should move back 2 revolutions, which we do. And if we went to a million counts, we'll be moving 500 different revolutions, and moving a bit quicker because we got past the acceleration time there. So that's the simple demonstration that we're doing for simple positioning. In addition to this screen, which is to help you test your result, there's also a detail screen here that you can look at. What's useful about this detail screen is it shows the current state of the network, and it breaks down the status word that's coming back from the motor, and it gives you the ability to read and write SDO messages by demand by typing in the index or where the data is located in the parameter map inside the smart motor, and then reading the result and getting the feedback there. So in this case, we had read the default acceleration for this smart motor, and that's the parameter there, 6083. It came back with a hex value of 1F4, which corresponds to 500 pulses per second per second. You also have the ability to write SDO data, and then there's also another screen that provides you all the status information that's been decoded, along with some of the parameters that we're exchanging with the smart motor in this case. So that concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, um, so we don't have a webinar next week as we will be at SPS Italia, but the following week we will have a return webinar on the Excel Prime series. I'm not seeing any questions in as yet on that one. Okay, in that case, as usual, if you've missed any webinars on the webinar page here, you can go back and watch all the past ones. They'll all get uploaded. Today's one will get uploaded by the end of the day, I believe. If you want to go back and watch any bits of it. So thanks for joining us this morning, and we'll see you in 2 weeks' time.